Okay, let's continue with the second half of the session. I welcome Claudia Hecht from the University of Regensburg, and she's talking to us about the phase field approach for shape optimization, and I think we've got some pre-boundaries in the torus medium as well, and so yeah, that's it.
So thank you for the introduction, and thanks to the organizers for giving me the opportunity to give a talk here. And as already said, I'm going to talk about a shape optimization problem in fluids in particular, and I'm going to introduce a phase field approach for this shape optimization problem. And I want to remark that this is a joint work with Harald Garke from Regensburg too. I'm going to start with introducing you to the setting. So the picture you could have in mind throughout this talk is the following. So we have this fixed container omega, which is this rectangle here. And inside this container omega, there may be some parts which are filled with fluid. And this is denoted by E here. So there's one part filled with fluid. And on the boundary of omega, we may have some boundary data on this fluid. So here you can see some inflow data and some outflow data. So this is the boundary data for this fluid. And what we do have additionally is some body force acting on the whole of omega, which may, for instance, be gravity. So that's the fixed data throughout this section, throughout this whole talk here. So this container, the boundary data, and the body force. And what we are going to try to solve is we want to minimize some functional by varying E. So that's the idea of shape optimization. We want to minimize a functional by varying the domain filled with fluid. And so the free boundary in this problem is somehow here the boundary of E, and that's the boundary that we can vary in this optimization process. And you see here the functional we minimize depends mainly on U and on the derivative of U, and U is the velocity of the fluid. So as we change the domain filled with fluid, also the behavior of the fluid changes. And the behavior of the fluid is in our case described by its velocity. And the velocity is denoted by U and is defined on the whole of omega, even so there's only fluid on a part of omega. And that's actually essential in this model. So we define U on the whole of omega by defining U to be 0 if no fluid is present. And if fluid is present, we just define it by fluid mechanics, and in this talk, these are going to be the Stokes equations. So that's the aim. We want to minimize some functional depending on the velocity of the fluid by varying the set where to put fluid and where not. And in order to formulate this in a more mathematical way, we use the following idea that you've already seen yesterday in the plenary talk of Klaus Deckelnick. So we use the identification of sets with its characteristic functions. And here we shift the characteristic function, so the design variable phi has values in plus and minus 1 instead of 0 and 1. And this is only due to this phase field approach, which will come in a second, but this does not change anything here. And the design space we use is BV of omega, so this means that our design variable phi is in L1, and the distribution or derivative is a finite Radon measure. So then we have this correspondence of phi in BV, and the fluid set is then a Katsopoulos set. So that's the setting we're working in with. And now shape optimization problems are generally known to be not well posed, which means that we are searching for a minimizer, but in general no minimizer does exist. And so we use another idea, namely a regularization. As we've seen yesterday, we add here a perimeter term. So we add here to the objective functional a multiple of the total variation of the derivative. So the derivative is a measure, that's the total variation, which is the so-called perimeter, and C0 is a positive constant. And if the set, this fluid region, E of phi, is smooth enough, then this total variation here equals exactly the area of the free boundary. So in this sense, we somehow regularize this shape optimization problem, first from a geometric point of view, we want to have a finite area of this free boundary, and also in an analytical point of view because we have nicer compactness criteria like this. And so summarizing this optimization problem looks like this. So we want to minimize this objective functional plus this regularization over all couples phi and u, and of course phi and u are connected by a fluid mechanical system. So to be precise, we want the Stokes equation to be fulfilled in this fluid region, whatever this means. And the example that you could think about in the following, the typical example used here is the total potential power, which is just mu over 2 du squared. So mu is the viscosity of the fluid, that's a constant, minus the work done by the external force. So that's the typical example you could have in mind here. Now I have to tell you what it means that the Stokes equations are fulfilled for u and the set where phi is 1, because recall that the set where phi is 1 is only a Katsopoli set, so roughly speaking Lebesgue measurable. And so we cannot write down the classical PDE as we would do it for some open set. And we do this as follows. So the weak form of this equation is as follows. We want to find a velocity u in this fluid dynamic space. So we have this boundary data and we have incompressible fluid, but we want u to vanish outside the fluid region. And u has to fulfill this elliptic PDE for all test functions in the corresponding homogeneous space. And this is just an elliptic PDE where you get solvability. So for each phi in L1 fulfilling some conditions, you have a unique solution u corresponding to phi of this equation. And we will denote this by S0 phi. So this is our solution operator. For every phi, we get a unique solution u. And now I did skip a little bit fast the condition which has to be fulfilled for phi in order to have a solution, but this condition is quite essential. So of course you have the solution space where you find your solution has to be non-empty. And this is sufficient for having a solution, but it's not trivial because you have non-zero boundary data, but you require u to vanish in certain parts. But if this is consistent, these two conditions, you have a solution. So now we have the solution operator S0 of phi, and we can rewrite our problem in a reduced form. And this looks now like that. So we minimize J0 of phi, and J0 is just the objective functional plus this regularization. If phi is in our design space, u fulfills our state equation, and additionally, I did not tell you before, phi has to fulfill some integral constraint. So this means that we prescribe a maximal amount of fluid that can be used for the optimization process. So this can be included in this setting here. And otherwise we just define it as infinity. Now this is a very nice problem because you, roughly speaking, optimize over all Katsopoli sets, or all Lebesgue measurable sets. So you do not prescribe too much regularity on your optimal shape. You do not prescribe geometric constraints, and in particular, no topology is prescribed. So you can also change the topology in this optimization process. So that's why you also call this shape and topology optimization. But on the other hand, this problem is also difficult to handle numerically and to carry out certain aspects in the analysis. And so in the next step, we want to approximate this by more regular problems, which still inherit all relevant geometric properties and reflect all relevant geometric properties and allow topological changes. And so we can still have this large class of possible solutions. And so the idea therefore is this phase field approach that you've already seen yesterday a couple of times. And I'm going to show you what it means in this setting, how we can include here this phase field approach. So recall this picture. Here we have our fluid region is where phi is 1, and here's the region outside of the fluid, so there's phi equal to -1. And what we do now is we replace this free boundary here by an interfacial layer of small thickness related to a small parameter epsilon. So we insert here a small transitional layer. And what happens is the following. So our design function phi looked like that. So we had a jump between -1 and 1. But now if we insert this small transitional layer, so that's in a 1D picture, if we insert here the small transitional layer, we can allow a smooth transitions between those two regions, phi 1 and phi equals -1. And that's the idea of obtaining more regular problems. And that's essential all. You can directly formulate the problem in this phase field setting. So that's the next slide. So the function that we minimize now depends on this interfacial thickness epsilon. We still minimize this objective functional f depending on the velocity, but now we choose phi in h1 of omega and allow values between -1 and 1. U has to solve some state equation and phi has to fulfill this integral constraint, so that's still the same. But before we added here the area of the free boundary, but now we replace the free boundary by some interfacial area, and so we also have to replace this area functional. And we replace this by this Ginzburg-Landau energy, since this energy is known to be a diffuse interface approximation of this area functional. And this is a gradient of phi squared plus 1 over epsilon psi of phi, and psi looks like that. And important is that psi vanishes exactly at -1 and 1. And so as epsilon becomes smaller and smaller, this term ensures phi to have only the two discrete values, -1 and 1. Now before we stated also for the velocity to vanish if no fluid is present, but now we somehow smeared out the interface, so we do not know what it means if fluid is present or not, so we have this diffuse interface setting. So instead of requiring U to vanish in certain parts, we add a penalization term to the objective functional. So we add here alpha of epsilon of phi U squared, and alpha epsilon looks like that. So at -1 it has a very high value, alpha epsilon bar, and at 1 it's 0. And this means if you're outside the fluid, so phi is -1, alpha epsilon has a very, very high value, and so this term ensures that U has a very small modulus in these parts. So in this sense, this term approximates U to vanish outside of the fluid region. And otherwise we just define J epsilon to be infinity. Now this is the problem, but I have to tell you what it means that U solves these equations. So you see here that the solution operator depends on epsilon. So we have here different state equations, and they look like that. So the state equations for epsilon greater than 0, we still want to find the velocity in this space h1g sigma, and we have here this elliptic PDE where now this term alpha epsilon appears, but we do not require U to vanish in some parts, like I already said. Now this equation can be understood as follows. So if you're inside your fluid region, phi is 1, then this term vanishes and you just have your Stokes equations. And if you're outside the fluid region, then this is again constant, alpha epsilon is again constant but has a very high value. And then this equation describes fluid motion through porous medium. So here we have this porous medium appearing, and so we somehow relax the condition of non-permeability outside the fluid region. We have now a porous medium with small permeability. But for this equation you get again solvability. So for every phi in R1 we have a Unix vector field U corresponding to these equations, and that's our solution operator S epsilon. And remark that the state equations do depend on epsilon additionally, so that's makes the problem technically challenging, because in the next step we want to consider what happens if epsilon tends to 0. So do we really approximate the original shape optimization problem, or is it just a good idea? And this is of course the next topic. So first of all, we do obtain a minimizer for every epsilon greater than 0. We have a minimizer of J epsilon, which is important because in shape optimization, like I said, you do not have existence of a minimizer in general. You also obtain a subsequence that converges in L1 to some limit element. And now the question is if phi 0, which is the limit of those minimizers, minimizes J0. So this would be really good, because then we do have an approximation. And this is true in two cases. So if either this convergence here happens at a certain convergence rate with respect to epsilon, or if the specific objective function, so the certain energy here is used, then you can show that the limit element phi 0 minimizes J0 and the minimal functional values converge. So in this sense, we do have an approximation of the original problem in those two cases here. And so this is the total potential power that you've seen in the beginning, which is an important application example. But now we're talking about optimization, so the next step is to consider optimality conditions. So of course we want to do numerics too, so we have to talk about optimality conditions. And this is a geometric problem, so optimality conditions means here we want to consider geometric optimality conditions. And I briefly sketched the idea here. So what we have is the following. So assume we have this fluid region where phi is 1, and then we deform this fluid region in direction of some smooth vector field V, And if now this fluid region is optimal, then of course the objective functional will have a greater value of the objective functional if phi epsilon is the minimizer, and that's how you obtain the optimality conditions. And this you can do for both epsilon greater than 0 and equal to 0, and I did write it down for both simultaneously, but of course in the analysis you have to distinguish because those problems are mathematically quite differently. But you can carry out this in both settings. And just to make a connection to existing results, so what would you do classically in shape optimization is shape derivatives, like this Hadamard structure theorem. So there's some classical theory how you would derive optimality conditions, but you always need a regularity on your minimizing set, like C2 boundary of the free boundary. But recall, here we do have a Cacciopoli set, which is roughly a little bit better than Lebesgue measurable, so no regularity. But if you assume the regularity necessary for deriving the shape derivatives, then of course those optimality conditions we derived here are equivalent to these classical results. So here we are consistent with existing ideas, and additionally the problem, this phase field problem, is in some sense a classical, or not classical, but it is an optimal control problem. And optimal control problems you solve classically by parametric variation. So you carry out parametric variations and obtain a variation inequality. So that's what you've seen yesterday. And you can show if you have this variation inequality, then also the optimality conditions derived in this geometric setting here are fulfilled in the phase field setting. And so in this sense, we do have consistent optimality conditions with existing approaches. And of course, we still have the question, what happens to the optimality conditions if epsilon tends to 0? And this will be included in the next summary, but before I want to show you here this just a brief form of the optimality conditions, how they look like. So the previous slide looked quite easily to calculate this derivative. So it's like, okay, you differentiate it with respect to t, but of course there's some work behind it. So here the differential with respect to t looks like that. You have some terms from the objective functional, you have some terms from this term alpha epsilon, and you have some terms from this Ginzburg-Landau energy, which regularizes this problem. And the crucial point is here to prove the existence of this derivative, so to consider the state equations and show that they are differentiable with respect to this parameter t. And then you have some PDEs, so linearized PDE, and the Stokes equation. So it's a quite difficult calculation here, just to show you this. But now we have shown the following results. So we already know that we have minimizers for every j epsilon. And we also have that for a subsequence, those minimizers converge as epsilon tends to 0. And we already know that if a certain convergence rate is fulfilled, then the limit element minimizes j0, and also the minimal functional values converge. And what we did show now additionally is that certain optimality conditions are fulfilled, and we can also show that the optimality systems which can be obtained by similar calculations do converge as epsilon tends to 0. Now this is very important because you solve those problems numerically, and numerics are based on first order optimality conditions. And if you now know that those optimality conditions really converge as epsilon tends to 0 to an optimality system for the original problem, you can really expect the solutions to be an approximation of your problem. And of course these optimality systems look a little bit more complicated, so you have some Lagrange multipliers for this integral constraints and some PDEs involved, but you can show that the optimality systems converge. And now you may ask, yes, so maybe this is possible because you have the Stokes equations, which are somehow the easiest equations in fluid mechanics, but actually you can also channelize this to different models in fluid mechanics, like the stationary Navier-Stokes equations, so nonlinear state equations where you have non-unique solvability. And under some suitable assumptions, you can, roughly speaking, say show the same results as before. You just have to assume something on the objective functional because of the non-uniqueness. And for the case of minimizing the total potential power, these conditions read as having small data or high viscosity as in classical results. So this is necessary because you have your sequence phi epsilon, u epsilon converging somewhere, and you have to identify the limit, and that's why you need unique solvability of the state equations in the minimizer. And so that's the condition here. And of course it's also interesting to measure different things for fluids, so for example the pressure. So far I did only consider the velocity, but you can also include pressure functionals because that's an important quantity for fluid mechanics. And if you want to minimize a functional depending on the pressure, you have to include an additional constraint. So you have to assume that in every part that you measure the pressure, there is fluid present. And the reason is that before we had the velocity vanishes if no fluid is present. And so you know what the velocity is doing outside the fluid region. But you do not know what the pressure is doing outside the fluid region. And so you have to include it. You can only take the pressure into account if you know there is fluid present, because otherwise it's not a relevant quantity. But then you can again show the same results. And in the end I'm going to show you some numerical pictures. So I a little bit motivated this phase field approach because the numerics are more easily. And actually some colleagues in Hamburg from the group of Michael Hinze, Christian Kali, who's also here, did do the numerics, and this is the first the result from the first example you've seen in the beginning. So that's the optimal configuration. So red is fluid in this case, so it's a little bit confusing maybe. So that's the optimal configuration in the example I've been showing in the beginning. On what we try to optimize here is an obstacle in a fluid, and this looks like that. And of course if you use the stationary Navier-Stokes equation and higher Reynolds number, you get more this wing shapes that you are maybe familiar with. And hereby I finish my talk, and thank you.
Thank you, Claudia. So are there questions? May I ask a stupid question?
There are no stupid questions.
Maybe this confused me from the beginning, because why do you in the first place need to introduce phase field models? Why can't you do all of this with sharp interface?
So the sharp interface model, so it depends what you want to do. So numerics, then you would have to use something like level set methods or something, but then you have a restriction on regularity or on the topology. And for this phase field method, you really have this large class where you do not have to restrict anything. And for the analysis, the problem is that you do not even, so you cannot even show existence of a minimizer in this general setting. So this is still an open problem, and is not even true for a general objective functional that you have a minimizer. Okay. But for this epsilon level, you have a minimizer, and it's really easy to treat because it's an optimal control form then.
Yeah, I was more confused with the topological transitions you would have, but why do you not want to have a topological transition?
Yeah, I should have shown a video here. So we did an optimization where you start with if you have, for example, here more inflows and here more outflows, and you just start randomly. It's not clear how the inflows and outflows are connected. Yeah, okay. And if you now allow topological changes, you really get an optimal configuration here, for example.
Boundary conditions for the flow, what kind of boundary conditions did you?
So that's Dirichlet boundary conditions, yeah.
Also on the free band,
No, so on the free boundary I do somehow impose, in a weak sense, Dirichlet boundary condition 0. So here I have Dirichlet boundary condition 0 in a weak sense, yeah.
But you could use other.
In this formulation, no. So in this formulation, the Dirichlet boundary conditions are essential. Yeah.
If there are no further questions, then let's thank Claudia again.